The integral test. Objectives. By the end of this lesson, you should be able to use the integral test to determine if a series converges or diverges. Alright, let's look at the formal statement of the integral test. If f of x is a positive, continuous, and decreasing function, such that f of n is the same as a sub n, for all n values at least as large as some threshold value big N, then the infinite series, the sum from big N to infinity of a sub n, and the integral from big N to infinity of f of x, either both converge or both diverge. So in other words, the infinite series and improper integral behave the same way, as long as they're both going from the same lower limit of integration, and here from the starting index of the summation. So in order to apply the integral test, I do need a series, I do need a function that is always positive, and then I would need that function to be continuous and decreasing in order to apply this test. Alright, let's do the first example. Use the integral test to determine whether the sum from n equals 1 to infinity of n over n squared plus 1 converges. So before we do this problem, let's talk about when to use the integral test. The answer to that is last, dead last. So before you try the integral test, you try everything else first, starting with the nth term test, and then remember, if it's geometric or harmonic, then since this is a positive term series, we could try the limit comparison test, the direct comparison test. We want to try everything else before we try the integral test, because it is going to be a lot of work. But because this one says use the integral test, we're going to use the integral test. So we're going to, instead of solving this series, we're going to solve the improper integral, so the integral from 1 to infinity of, instead of using n's, because we solve integrals with x's more often, I'm going to write this as x over x squared plus 1 dx. So the first thing is to rewrite this improper integral as the limit as r approaches infinity of the integral from 1 to r of x over x squared plus 1 dx. And so now, to solve this definite integral, I'm going to need u-substitution. So I'm going to let u be x squared plus 1. So du is 2x dx. And I only need my x dx, so 1/2 du is x dx. Now, since this is a definite integral, I am going to need to change my limits of integration. So u of 1 is 1 squared plus 1, so u of 1 is 2, and u of r is r squared plus 1. So now this becomes, so this was my scratch work here, so this is now the limit as r approaches infinity of 1/2 the integral from 2 to r squared plus 1 of du over u. Alright, so now this has a nice antiderivative at least. This is the natural log of the top limit of integration over the bottom limit of integration. So we have r squared plus 1 over 2. And with the 1/2 in front. And we're evaluating this limit as r approaches infinity. Alright, so now as r approaches infinity, the r is in the numerator in here, so r squared, so this is getting really big. The top's getting bigger faster because 2 stays the same on the bottom, so what we're really trying to think about is natural log function as r goes to infinity. Well, the natural log function grows bigger forever. It grows slowly, but it grows bigger forever. So this is infinity. So this improper integral diverges. So since this improper integral diverges, we can say that the series by the integral test also diverges. So that's it for applying the integral test to this particular series. So realize it did take quite a significant amount of work. We needed to use a u-substitution in order to solve this improper integral. But at the end, whatever behavior the improper integral has, we can say that the infinite series has as well. Alright, second example, use the integral test to determine whether the sum from n equals 1 to infinity of 1 over n squared plus 1 converges. So we'll set up the integral from 1 to infinity of 1 over x squared plus 1 dx. So this is the limit as r approaches infinity of the integral from 1 to r of, I'll write this as dx over x squared plus 1. So now no u-substitution needed, but we do need to recognize that this is an arctangent function. So this is arctangent x evaluated from 1 to r. So now we have the limit as r approaches infinity. So now we substitute in r and substitute in 1. So the limit as r approaches infinity of arctan r, plugging in r first, minus arctangent 1. Alright, so arctangent 1 is pi over 4. So arctangent, remember, is what do I have to plug into tangent to get out 1? So this is pi over 4. So now it comes down to what happens as r approaches infinity of the arctangent function. So this is kind of tricky. It's all about knowing what the graph of arctangent looks like. So arctan, or tan inverse, has two horizontal asymptotes at pi over 2 and negative pi over 2, which I'm sure you all know. And it looks something like this. It looks like the cube root function with these asymptotes, though. So that means as r approaches infinity, way over here, arctangent is getting closer and closer to pi over 2. So this value here is pi over 2, and I'm subtracting pi over 4. So this is a finite number, so that means that this original improper integral converges, right? So pi over 2 minus pi over 4 is pi over 4. It's a finite number, so this converges, and so the original series converges. So by the integral test, the series converges. So this was kind of a tricky one. Was the arctangent function. We needed to know what arctangent looked like as r went to infinity. So just a little bit tricky because of the inverse tangent function, but ultimately the integral test is again a test that I want to use absolutely last if I can't use some other test like direct comparison, limit comparison, the p-series test. But it will always work, and those tests, I should say, are based on the integral test. So if you happen to forget the conclusions of those other tests, they actually are derived from the integral test. So this will always work, but it may not always be the nicest because of sometimes the trickiness of the integral that we're trying to solve.